So there are many instances where you can turn a problem into a graph problem. So for example, imagine if you're in a maze and you're trying to figure out if it's even possible to escape. Every XY coordinate is essentially a vertex, and the edges determine if there's a path to get there. If there is a wall between two positions, then there's no edge between them. So now, once it's a graph problem, it's actually pretty simple. Most of the time, to solve a problem, you either have to visit all nodes, find all nodes reachable from a specific source vertex, or find the shortest path from one vertex to another. For our maze problem, we can find all nodes reachable from the source vertex to see if our destination node is even in the set of reachable nodes. If you want to figure out how to get out of the maze as fast as possible, you'll try to find the shortest path from our source vertex to the destination vertex. If somehow there are fruits around the maze and you have to figure out how many fruits in total there are in the maze, then you have to visit all the nodes of your graph and collect them. All those three things you did are basically exploring a graph, and there are two main ways of exploring a graph: breadth first search and depth first search. Today, we'll be learning how to do breadth first search, or BFS for short. Intuitively, the breadth first search is an algorithm that, starting from the source node, will check everything one edge away, then two edges away, then three, etc. So how do we implement this? We will keep exploring vertices and discovering its adjacent vertices. So for example here, the vertex we are exploring is 0, and we just discovered 1, 7, 3, and 6. The key to BFS is to use a queue to store vertices that have been discovered. The vertices stored in the queue will later on be explored to further discover other adjacent vertices. And every time you discover a vertex, you mark them, so you won't explore them more than once, since you could get into an infinite cycle if you keep exploring the same vertices. So as we discover 1, 7, 3, and 6, we are marking them and adding them to the queue. The vertices filled in red means that it's marked. Now, the next vertex to explore is 1, because it's at the front of the queue. 1 has 4 adjacent vertices, but you can see that 0 and 7 are already marked. So we don't add them to the queue, we just add 4 and 2. Next on the queue is 7. This time, all of the adjacent vertices are all discovered, so nothing to do here. Next, we have 3. We still have 1 undiscovered vertex, which is 5, so we add that to the queue. And we keep doing this until the queue is empty. Okay, let's write our BFS code. So V0 will be the given vertex where we start doing the BFS. We create a new queue so we can store the discovered vertices. Then we have to mark all vertices as undiscovered. You can do that within the node itself, or you can have a hash map where the vertices are the keys and a bit that tells you it has been discovered or not. Once you marked all the vertices as undiscovered, you usually have the first vertex as input parameter. We'll call that vertex 0. You'll add that vertex to the queue and also mark that vertex as discovered since you don't want to explore it again. Now, you will loop while your queue is not empty. What you'll do is dequeue a vertex from your queue. In our case, it's the first vertex, but later on, it will be the other ones. You will then explore that vertex. For exploring, you will loop through all the neighbors of your current vertex, which is easy if you have an adjacent list. Then, for each neighboring vertex, you will check if it has been discovered yet. If it hasn't, then you mark it as discovered and you put that vertex into the queue. That way, your queue is refilled with vertices you need to explore. And that's pretty much it. What would happen next is, after exploring the first vertex, you'll start the next iteration with the next element in the queue. So using our graph example, we've explored 0, which allowed us to discover 1, 7, 3, and 6. So those are in our queue now. Now we dequeue, so we get 1. We will explore 1, so we get 2 and 4, but not 3, 7, or 0. As you can see, those 3 have been marked as discovered, so we're not going to put them in our queue. We're only going to put 2 and 4 into our queue. Now we explore the next vertex in our queue, which is 7, but all of its neighbors are already discovered, so we're not going to add anything to our queue. Next, we have 3, and the only undiscovered vertex is 5, so we add that to our queue. Now, if you look at the graph, all of our graph has been discovered, but not explored yet. So if we fast forward, we are just going to explore the rest of the vertices in our queue, and none of the vertex will give us any additional vertex to explore since we've discovered all of them. And then once the queue is empty, we are done. So that's BFS for you, and as you can see, because of the property of the queue, which is first in, first out, we're able to explore the graph in a way that explores your surroundings first before going deep. In the next video, we'll go deep first before exploring our surroundings, which is going to be the depth first search. All right, I'll see you next time.